Imagine logging into your school portal to check your recent assignments, but instead of the usual teacher feedback, you find empty fields, and your final grade has shifted from a B to a D. When data is modified without authorization, the integrity of the entire system is compromised. These specific alterations indicate a targeted effort to manipulate the database and its stored records. Look at the interface. That red privacy banner and the sudden drop in the grade field suggest the application has processed an unauthorized request. These are the visual markers of an application layer attack. Every minute this goes unreported, an adversary stays logged in. They use that window to map the server's internal structure, searching for even more sensitive databases, while their presence remains hidden. Stopping that progression requires detection, the active monitoring of networks and applications to identify unauthorized access and malicious behavior the moment it occurs. Without these monitoring tools, private user records can be exfiltrated and software security protocols bypassed without a single alert being triggered. Security professionals view these threats through the CIA triad: confidentiality, integrity, and availability. This diagram shows how a central shield blocks red corruption. Detection serves as that shield, protecting the core data from being altered or stolen. By catching an intruder during the initial access phase, defenders can isolate the threat before it spreads from a single student's account to the entire school's database. If you spot unauthorized changes in your own accounts, do not try to investigate the source code or logs yourself. Report the incident to your IT department immediately. Then stop using the suspicious application. Continuing to interact with the interface can send more of your data directly to the attacker's session. Finally, change your passwords. You must do this from a separate, trusted device, like your phone, to ensure the attacker isn't monitoring your activity. This move allows the IT team to begin their investigation from the monitoring dashboard. Following this response policy prevents you from accidentally aiding the attacker and preserves the digital evidence the IT team needs to reconstruct the breach. That reconstruction begins with accounting. Servers maintain audit trails, meticulous records detailing which accounts access specific data and the exact time the connection occurred. On this server log, the 2 a.m. timestamp aligns with a sudden spike in failed login attempts. This pattern suggests an automated password attack is attempting to brute force its way into the system. Application logs track commands typed into search bars, revealing the exact exploit method. Here, the input contains the string -- or 1 = 1. This code is used in SQL injection attacks to bypass password checks and trick the database into revealing sensitive data. By analyzing these entries, IT professionals translate invisible digital actions into a concrete timeline, proving how and when an adversary breached the application. With the timeline established, defenders must determine exactly which records were altered while the attacker had access. File integrity checks provide the answer. Scanning a file generates a cryptographic hash, a unique alphanumeric fingerprint. If data changes by even one character, the hash changes completely. Comparing these strings provides mathematical proof that document B has been altered. While hashing audits files after an incident, organizations use active traps called honeypots. A honeypot is a decoy file, like admin passwords, designed to attract intruders. No legitimate user has a reason to touch this file. Interacting with the honeypot triggers an immediate alert, identifying a malicious actor in real time. Combining mathematical proofs, like hashing, with active traps, like honeypots, creates a layered detection web that forces adversaries to reveal themselves. Once the intruder is detected, the IT team isolates the compromised database, cutting the connection to prevent the attacker from downloading any more records. Then they apply corrective controls. They restore the application and its data to its exact state from a clean backup recorded before the breach. This restoration process overwrites the attacker's unauthorized changes. As the bar fills, the corrupted data is replaced by verified records, fully restoring the integrity of the database. Effective recovery is only possible when early detection gives defenders the time they need to isolate and restore these systems. Protecting data requires 5 specific actions: identifying suspicious activity, auditing access logs, verifying integrity with hashing, deploying honeypots, and following a safe reporting protocol. These tools, audit trails, hash comparisons, and decoy files, allow IT teams to pinpoint exactly where and when a breach occurred. Let's review. Which record builds a timeline of digital actions? Where should you reset a compromised password? And what generates a digital fingerprint to prove a file hasn't changed? Access logs build the timeline. Passwords must be reset on a separate, trusted device, and cryptographic hashing generates the fingerprint to verify file integrity. Whether targeting a school portal or a global database, detection stops a threat before it reaches the most sensitive records in the system.